Normally I would thank the organizer, but I think it's not much appropriate. So thank you very much for the presence of all of you here in our university. It's a pleasure. I will, before I start my presentation, I will remember you that we will have the event photo just after the coffee break. So, okay, I'm gonna talk about, I will try to tell you a story of a problem that started by the end of the 50s and seemed to be solved by the beginning of the 70s. But in fact, it was not solved. And the problem is, as was said by Nathan, to compute the topological of endomorphisms of Lie groups. And I will start with the following formula, which is a very famous formula. When I was in a conference in 2000, I think 2011, in Campinas, an international conference in topological dynamics, Marcelo Viana talked about this kind of issue, this kind of topic. And he started with exactly with this formula, which is a very famous formula in ergodic theory, called Bowen's formula. Was proved by Bowen in the beginnings of the 70s, which says the following. We start with G connected Lie group, and phi is a continuous endomorphism of G. Okay, and the formula says the following. The entropy, it's denoted by H, the entropy of phi is given by this sum here. The sum of the logarithm of the absolute value of lambda the lambdas which has absolute value greater than 1, okay? There is a D here, and this is the reason why this is not, in fact, I will show soon. This is the reason why this is not the topological entropy, in fact, okay? There is a D here, which is a G invariant distance, okay? And lambda, these lambdas are eigenvalues of the derivative of phi at the identity. Okay? So this is a very famous formula. And in fact, this is a generalization of a previous formula for the endomorphism of the torus. And it seemed that this topic was already solved in the beginning of the 70s. But in fact, this is not the case. Why? Because there are three types of entropy. First of all, what is entropy? Entropy, in a roughly sense, is a measure of the complexity of the dynamical system. Okay, it's an invariant, a dynamical invariant, topological. In the case of topological entropy, is a topological dynamical invariant, and measures the chaotic behavior of the degree of the chaotic behavior of the dynamical systems. Roughly is this. But there are at least 3 ways which we can define the entropy. And this is related to what we call the variational principle. Variational principle.
Mauro, excuse me, I don't understand.
Okay.
What's
HD is the notation for the one of the 3 types of entropies, which I will explain just here. But in the definition of this entropy, we need to prescribe first a distance. Okay. And so this is not exactly the topological entropy. But why people thought that this is the answer for this problem? For the following reason. First, appeared a definition of entropy, which depends on a phi invariant measure. This is the first concept of entropy introduced by Kolmogorov and Sinai in the end of the 50s. Okay, then appeared another concept, which is in fact a topological concept because it's defined only using the topology of the phase space. The topology of the Lie group G. In fact, the variational principle is true and holds in a much more general setting that endomorphisms of Lie groups. It's for a continuous map in a topological space, basically, in a metric space. This definition was introduced by Adler, Konheim, and McAndrew in 1965. Okay? And after this, Dinaburg in 69, and then Bowen in the same paper, in the same article, defined another concept of entropy which depends on a distance. So we start with a metric space with a distance d, and we can define a concept of entropy. And what is what is the relation between these 3 different types of entropy? This is given by the variational principle. So it was proved, I think, in 69 and 70 by Dinaburg and Bowen. And they proved 2 things. First of all, when the space, for instance, the group G is compact, we have this equality. So for every distance we choose, these 2 are equal. Okay? They are equal. And
so that for every distance,
it's
given the same topology?
Yes, given the same topology, they are equal. Okay? Given the same topology, they are equal. And here is a little bit more difficult because you need to take the supremum over all the phi invariant measures. So this is the relation in the compact case. But my point here in this talk is to look what happens for a general group, which may not be a compactly group. Okay, and I will show an example which shows that this no longer holds. This equality is not true when G is not compact, when the phase space is not compact. And the example is one of the simplest example we can imagine. We take G, the multiplicative complex numbers, okay? And we take phi of G. G is, in this case, G is we have here 0, so is C star is the complex number without the origin. And we pick up this map. Okay, it's just the square of the okay, so we can compute the topological entropy using the Bowen formula, okay? The topological entropy, because now this guy is not compact, okay? We are here with a group which is not compact. In the compact phase, they are equal, but in this case, this happens. When you compute the derivative of this map, we get this, of course, okay? At the identity, okay? And so, Bowen's formulas, okay? This is the eigenvalues, so log of 2 plus log of 2, 2, log of 2, okay? But this is not the true topological entropy, okay? In 2010, and then with a student, André Caldas, in 2018, we correct this formula for the case of the non-compact metric space. So when you are in a non-compact metric space, you need to put here a correction, which is take the minimum. Okay, so we have something like this. There is here the topological entropy. There is here the Kolmogorov-Sinai entropies. Okay, right here. When you take the supremum, you get the topological entropy. But when you are in the non-compact setting, the entropy, which is defined using the distance, depends on the distance, not only on the topology. Okay, and we can see this in this case. For instance, we can look at the S1 here inside the complex numbers. If we take a complex number G outside or inside the circle, this map, what does this map? He does the following. He doubled the angle and we squared the absolute value. So something like this occurs. So if we are outside of the unit circle, things are not recurrent. The points when we iterate the dynamics don't come back to itself. Okay, so the recurrent set is inside the S1, and there is a very famous result in ergodic theory. One of the first results of ergodic theory, which is the Poincaré recurrent theorem, which said that the support of the fine variant measures lies inside the closure of the recurrent set. So the support of the invariant measures for this map are inside the unit circle. Okay. So if you know this, we can do the following. The topological entropy is the supremum of this guy, but this guy only see what happens inside the S1. So variational principle plus the Poincare recurrence theorem, we get this. The topological entropy using the variational principle plus the Poincare recurrence theorem, we get this. And here we are inside a compact Lie group. And thus, when we are inside the compact Lie group, the equality holds. And we can compute the topological entropy using the Bowen's formula. But now, here is the unit. The derivative here is just the number 2. It's not the matrix 2, 2. Okay? So we get half of the true topological entropy is, in fact, the half of which Bowen's formula will tell us. So, okay, these kind of low-dimensional examples led us to conjecture something, the following. Okay. Okay.
Why is minimum and not infimum?
Because when you know, if you take the distance induced by the one-point compactification, realized this infimum. So it's a minimum. Okay. And when the space is compact, every distance comes from the one-point compactification because it's without 1 point, because it's already compact. So, okay, this kind of example led us to some conjectures and some partial results. Okay. This is also with André Caldas, 2013. And we assume here that phi is surjective. As here, phi here is surjective. And we assumed first that G is abelian. Okay, so for example, this guy here, which is S1 times R, okay, is a cylinder. And the conjecture here is the following. The real topological entropy is the topological entropy of the restriction of phi to a torus. Which torus? The maximum torus. Okay, the maximum torus. So, G, if G is abelian, G is a torus times a vector space. Okay, so phi can be restricted to this guy here. Is invariant, always invariant. So this is the conjecture. In fact, when we look to the low-dimensional examples, and we look to the closure of the recurrent set of 5 of this guy, when G is R2, when G is the cylinder, which is this case here, and when G is the torus, what we get is the recurrent set here is just the identity, because is expanding and everything is expanding when, in this case, this map is just multiplication by 2, okay? Multiplication by 2. Because this is the additive Lie group. Here is that guy, so the closure of the recurrent set is S1, and here is the whole. Okay? And in fact, we proved this, but we proved this also for G nilpotent, and we proved this for when G is reductive. Okay, so this was our results. Everything is okay. These are nice partial results. But we got stuck. Okay? I will explain why we got stuck. But the problem was the solvable Lie groups. The solvable Lie groups are much harder to work, and we need to find a way to overcome all of the problems generated by the solvable Lie groups. The problem here, as we will see, is the solvable Lie groups. Okay.
An important and reductive case, E of G is the maximal compact torus.
Ah, sorry. I forgot to explain here. When we add, in this general situation, of course, G is no longer T times RK, but we take the center, the identity component of the center. So this was our conjecture, and this holds in this case. For instance, when G is semi-simple, the topological entropy is always 0. There is no topological entropy for endomorphisms on semi-simple Lie groups. This formula gives us just an upper bound. Just an upper bound. Okay? Okay. Then we managed to overcome all the difficulties, and we get, finally, the general result. We have been published last Friday on the digital form in Israel Journal. So, and the result is almost this here, but now we do not assume that phi is surjective, and we do not assume none of these, nor connectedness, nothing. It's completely general. So we get something like this. The topological entropy is the topological entropy of phi restricted to a torus, but not the torus of the entire group G. Is the torus of a subgroup, a connected subgroup of G, where phi is surjective. And it's maximum with this property. Okay, so there is, in fact, we can prove that this group is a closed group, but this is not very important, but there is a maximum connected subgroup where phi is surjective. So if you apply that formula for this situation, you get the actual topological entropy. Okay, I will give you an example to illustrate the result. The example is very geometrical. We can take G, the homotheties of R2. Okay. It's disconnected because there is a connected component of the identity, which is the orientation preserving homotopes, and the others, which not preserve the reflections and the connected component of the identity is just the affine bijections of C. It's very easy to see this. So the elements G now are maps of C on C itself, onto C, given by things like this. Affine maps, okay? These are the orientation preserving homotopes and it's easy to see that this guy is just the same direct product of C star to C. And here we made this identification. So G is identified with these pairs, the multiplicative constant and the additive constant. Okay? And we can consider, for example, an endomorphism here, which take phi AB and associate it to this pair here. So clearly phi, it's not phi, phi is not surjective, okay, because here is always 0. In this case, it's easy to see that G phi is C star 0. Okay. And by the above formula, we have this. But this guy is exactly this guy. Okay? C star times 0 is C star. Okay? And when we restrict this to this, is exactly that map. So we know that the topological entropy is log of 2. Okay? So this is a low-dimensional example. And here, we cannot apply the partial results because this is, besides this disconnect, this is not the real problem. The real problem here is that this guy here is solvable. So, okay? So now, my time here. Okay. So I will try to give a picture of, a sketch of the proof. Okay?
No center.
No center. No center. No center. But this guy here has center, which is, this guy is abelian.
So G5 is unique?
G5 is unique. G5 is unique. Okay. And it's closed. It's well behaved. So everything here goes much faster than there. So, okay. So just to give a sketch of the proof, and the proof relies strongly in the structure, the structure theory of Lie groups. This is what I want to emphasize here because we are in a Lie theory congress. So, sketch of proof, and the proof is a combination of 2 Li's and 1 Yorke. 1 Li from Lie theory, okay, and 1 Li from Li Yorke pairs. I will tell you what is this. Okay, so it's a story of 2 Li's and 1 Yorke. So the strategy here is to break the problem. Okay, you use structure theory to break the problem, and in smaller and simpler problems. This is the strategy. To do this, we need something like this, some results like this. For example, imagine this result was already proved by Bowen in that same article. It's an amazing article of 1970. But he assumes that G is compact, and if you have an invariant subgroup T, you can pass to the quotient, and you get another map, an induced map here, var phi, and you have the restriction to the T here. And Bowen proved the following. The topological entropy in the total space in G is a sum of the topological entropy in the basis plus the topological entropy in the fiber. So this beautiful formula here. So this would be sufficient for me to solve the problem if we were dealing with compact spaces, but we are not dealing with compact spaces. For example, this guy is not compact, this guy is not compact. So the first try here is to generalize this for non-compact groups, but there are a lot of technical problems because the definition of entropy is very difficult to deal with. It's not very easy, but we could get the following result. It's a much weaker result, which is the following. G may not be compact, but the fiber still has to be compact. Okay? We still have an invariant subgroup T. We can still induce here I put here TG instead of T because I will apply the abstract result to TG. And so we have something like this. The G is not compact, but the fiber is compact. So we are taking a fiber bundle with a compact fiber. Okay? We need to assume that phi is proper. So the inverse image of compact sets should be compact. And we get this. So this is a much weaker result because we have now an inequality. No, it's any compact. Here the situation is much more general, but I'm interested here in the application. So, but it's more general. Okay, and so, okay, I would like to prove the equality of D is equal to this. I will prove only in the case where phi is surjective and where G is connected. This is, in fact, the hard situation. Okay, so I will concentrate in this case. I would like to prove this. This equal to this. So there is a problem here because I have an inequality, okay, and there is this guy here, okay. But if I manage to prove that this guy is 0, okay, I get one of the inequalities, and the other is always true because this is a subset of G. So the other inequality is always true. So I need, again, I got stuck here because I need to take the quotient by non-compact Lie group, as we will see now. And now appear the Li Yorke, okay, which is the following. I will use the following concept, which is the concept of Li Yorke pairs, which is the following. X and Y are called a Li Yorke pair, okay? If they have the following very strange behavior, dynamical behavior. Sometimes they are very close to the original positions by the dynamics, and sometimes they are very close to another point. So sometimes they are very close to here, sometimes they... This is a chaotic behavior in the sense, if you take something very close here, but with some error, you do not know what will happen in the future, because sometimes, even if you get more and more close here, sometimes these points get far each other, and then they get close, and they get far. So this is the definition of. There is a definition. I won't put this now to get to save some time, but there is a relationship between entropy and the existence of Li Yorke pairs, which is the following. If the topological entropy is positive, so we have the existence of Li Yorke pair. And I would like to prove that this entropy is zero. So if there is no Li Yorke pair, I can use the contraposition, which is equivalent. So if there is no Li Yorke pair, maybe this is zero, and I'm done. Maybe this is zero, and I'm done. And it's much easier to deal with Li Yorke pairs than to deal with entropy. It's much easier. So I get the following result. L is an arbitrary Lie group. M is an arbitrary subgroup which is stabilized by phi. Okay, so we can look at the induced maps again, but now L is an arbitrary Lie group. M is an arbitrary compact, non-compact. Okay, and we get this. If the maps on the base and on the fiber have no Li Yorke pairs, then the map on the total space has no Li Yorke pair. So this was the key element to apply the structure theory of Lie groups. Because now I'm free to apply all quotients I want to get simpler and simpler problems and solve the problem. So I will go to the end. which is apply the structure theory of Lie groups. Okay, so I will start with this guy here, which I will call H. So I started with G, take the quotient of G by the torus, that torus. I will call this guy G, and I want to show that the topological entropy of the induced map here is 0. How I will show this? Showing that there is no Li Yorke pair for this map. Okay? This is the strategy, applying this result again and again and again, like a matriuska. So I start with H, and now I will not denote the maps, only the groups, the phase space, because there are a lot of induced maps. They are all induced maps. Okay, so I will consider this, and I will take a first quotient here, which is the following. I will take the quotient of H by its radical, solvable radical. Okay? So we get something like this. So the fiber here is R, the solvable radical of...
But H is not a group.
No, H is a group, because this guy here is a... I will take a lot of quotients by normal subgroup. So everybody here is group. Group. Okay? So this is a normal subgroup because the center is a normal subgroup, and these guys, it's not difficult to show that it's a normal. This result is normal and it's same simple. So I need to show that the topological entropy here is 0. Okay? There is no Li Yorke pair here. Okay? So I will try to show that there is no Li Yorke pair here, no Li Yorke pair here. If I get this, my result shows that there is no Li Yorke pair here. Okay? Okay. This is the first matriuska. Okay. In order to show that this is not has no Li Yorke pair, I will consider the following. So S is a semi-simple Lie group because I take the quotient by the solvable radical. Okay, and I will take aquí another quotient, which is the quotient of S by its center. Okay. Sorry. Center of S. Sorry. Okay, but the center of semi-simple Lie group is discrete. So it's impossible to have this behavior for a discrete topological space. If the space is discrete, there are no Li Yorke pair. Okay, there is no Li Yorke pair. So here we have no Li Yorke pair. No Li Yorke pair. And here we have a semi-simple Lie group, which is a linear semi-simple Lie group, because this is in fact the adjoint group of the semi-simple Lie group. And it's not difficult to show that some power of my original map is a restriction of a linear map. And linear maps, it's easy to show that linear maps has no Li Yorke pairs. So we get that this. But it remains the fiber. So I need to prove that in the fiber, this is the problem, because the fiber is a solvable Lie group. So what we do is the following. Another matriuska. I will take a quotient here. Here is important that the maximum torus of the center of this guy is trivial because I have already killed. Okay. It's not difficult to show that its solvable radical has a trivial maximum torus. Okay. And I will take the quotient by the new radical of R. And it's not difficult to show that this guy here has also a trivial torus. Okay? So here is a vector, topologically is a vector space, Okay? To link to this example here, now R is this guy here, okay? N, if R is this guy, N is this guy here. Okay? This guy. Okay, and we get here an abelian Lie group, and we will take a last one, Matriusk. Okay, but here we have a nilpotent simply connected Lie group, and every endomorphism of a simply connected nilpotent Lie group is conjugated to a linear map by the exponential. Okay, so again, we don't have Li Yorke pairs here. So we need to prove that there is no Li Yorke pair here to get here and to get here and to get here and to. So now is the hardest part, the technical part. I will take the quotient by the torus. This guy can has a torus. Can have a torus. This guy is this guy. Okay. When I take the quotient this of this, it remains this guy here. There is a torus which is S1. Okay. In this example, okay, in this example, this is the general case. And here I have a vector space, so an endomorphism here is a linear map, and so there is no Li Yorke pair. And the hard part is to show why there is no Li Yorke pair here. In fact, we can show that the induced map here has a finite order. But it's very difficult to prove this. I need a result to prove this. It's a very technical 4 pages to prove this, and I need a result which I didn't know previously, which is in the book of Neb and Hilgert, Geometry and Structure of Lie groups by 2012, which is the following: a characterization of the center of a connected Lie group by spectral theory. It's very interesting. It's very interesting. Fundamental theorem of the center. So after a lot of work, we can imagine to prove that this guy here has finite order, and so no Li Yorke pair. So no Li Yorke pair here, no Li Yorke pair here, and we prove a result. So it's a long way. So Okay, so I will finish just with three final remarks. Which are the following final remarks. First, open questions. Né? An open question which is trivial in the compact case because we have this formula is to compute, start with a non-compactly grouped G, okay? Take H and not normal subgroup, okay? But which is stabilized by the endomorphism. Consider the induced induced map. What is the topological entropy of the induced map? H closed, but H. This is very hard if G is not compact, even when the H is compact, even when because we have only this inequality here. We have only so. I can get from this inequality a lower bound for H phi, okay? But and it's even worse when H is not compact. So take a non-compact Lie group, take a lattice which is non-compact and fixed and consider the induced map. It's a very hard problem, I think, but it's an interesting problem. It's open. Because people are normally, in the 70s, concerned about compactly groups. But there are a lot of interesting things related to non-compactly groups. Even if the quotient is compact. Because G can be compact, H non-compact, and the result is compact. Even this is open. Second, by my result, it's immediate from my result that the topological entropy of endomorphism doesn't see the connected components of the Lie group. All the information is inside the torus, which is inside the connect component. Okay, but we can consider these maps. This is my last remark. Power maps. The same power map which I started. When G is abelian, this is an endomorphism. But when G is non-abelian, this is not this is no more an endomorphism. But it's interesting because I'm finishing a paper about this, and in this situation, the topological entropy of power maps, only groups, see the connect component. So it's not always true that this still holds. So it's more interesting in this sense. But this is another story. I will stop here. Thank you very much. Okay. You consider the derivative of phi at the identity, and we look at the images because it's finite dimensional. In some step, it will stabilize, and this is the Lie algebra of the G phi. It's not obvious that the G phi, because G phi is the connected Lie group generated by this Lie algebra. It's not very clear that it's already closed, but we can prove it's in paper that it's already closed, a closed subgroup. But it's not very important for the results, but it's an additional result.
What happened with automorphism?
With automorphisms, this is, it's a particular case, but with automorphism, first, G phi is always G. Okay, so with this in mind, it's the same. And if G is a simply connected Lie group, this is always trivial, and the topological entropy of automorphisms in simply connected Lie groups is always zero. Always zero. This is a corollary.